Okay, here we are once again. This is the Natural Science video lecture. Natural Science 116, video lecture 3. Okay, we'll start off with some announcements and then I have a bunch of stuff to show you. See how far this goes today. Okay, first of all, we had some very good feedback with the notes being sent in on the video lectures. I had a couple of butter candles, so that's pretty gratifying to see. I hope you guys were as thrilled as I was. Okay, so this seems to be working well in terms of the notes being taken and sent. And my other big classes, I'm in the big lecture hall, by the way, where I teach 2A, and they're sending in all kinds of notes as well. So keep taking notes, take good notes. Take them twice, send them in, and I'll give you a number of things to look up online too to make your book nicer. Okay, yeah, so this is the week that's to come, Monday through Friday. Tuesday is actually a day off, Chavez holiday, for Tuesday, Thursday classes. But yeah, I'm still going to publish 2 lectures, and this is one of them. So we'll have 3 and 4. Video lecture 3 and 4 this week. Yeah, I want to start with some demonstrations. So I had mentioned some of these in the first lecture and in the second lecture. There's an interesting heat transfer by conduction demonstration that I'm going to start off with. I have it on the table here. And interesting phase transition one. Then we'll talk about the Arizona Meteor crater. And make our way into the heat engines. So we'll see how far we get. Heat transfer, first of all. So anyway, these are the aluminum, wood, and another pair of aluminum and wood blocks. This one was made by John Beckman some years back. And this one is made by our current shop guy, Dave. And yeah, aluminum and wood, and the point is that they've been stored in the same cabinet since the beginning of time. So they're at the same temperature. Although the first thing I do if I pass these out through the class, then this one feels very cool. Hold it up against your cheek, it's very, very cool. This one feels neutral or warm. And so why is that? Why does one feel cool, the other one feel warm when they have exactly the same temperature? They've just been sitting like this forever, okay? So, has to do with the thermal conductivity of aluminum versus wood. And what we do is we just place some ice on the wood here and some on the aluminum, and we don't have to wait long. Okay, we don't have to wait long at all. So we'll be a little bit patient, because we'll see in real time the ice on the aluminum is just starting to melt, and there will be no time at all before it's pretty much completely melted. And on the other hand, the ice on the wood is really doing nothing. Okay? It is doing nothing at all. It's not even leaving a drop behind at the moment here. Whereas both of these are turning into their own little puddle. Okay? So what's going on there? You're gonna have to refer back to the old notes, or should I draw this? What's going on is we have 2 objects, one at a higher and the other at the lower temperature, T hot and T cold. And the energy is flowing from hot to cold. It is flowing from the aluminum, which is room temperature, into the ice, which is 0 degrees or less. Okay, from the aluminum into the ice, melting it really nicely. These again, there's nothing going on here, barely a drop of water. Okay, this is a demonstration you guys can do without having some machined objects here of the same size and look. You could take ice on a wooden cutting board, ice on a ceramic dish, ice on let's say a cast iron skillet, and you'd have 3 different experiments, and you can see which one melts faster. Okay, so that's a good homework idea. How about you guys do that and maybe film it, or take a picture of it, or at least just do it and take a picture of it, have it for your notes. You can do this yourself, in other words. You've got wooden cutting board, you've got ceramic, which represents glass. You've got a cast iron skillet, and you'll get these different melting rates. Okay, so there you have it. Here, barely a drop. Same on this side. Here, both of these pretty much completely gone. So the energy was flowing out of the metal into the ice because room temperature is higher than 0 degrees Celsius. Okay, there you have it. Okay, that was a success. Let's see if we can keep that up. Okay, all this filming here, one take, no edit. Okay. Okay, that's nice. So we got that done. Now my next demonstration is going to involve soda can and a dish of water and a torch. So even though you don't have the torch and some tongs, you don't have the torch at home, but if you have a gas burner, you'll be fine. On gas burner on your stove, you can do this demonstration as well. So what I'm going to do is put about a ½ inch of water in the dish here. Half an inch of water, and you want more an inch. And surprisingly or not surprisingly, there are no paper towels in here to clean up spills. What's going on? Okay, so that is a dish with water in it. And here I'm going to put in about a ½ an inch of water in this can. You don't want too much, you don't want too little, so let's see how this goes. So what are we trying to do here? I'm going to boil the water in the can, and I'll know it's really boiling because steam will be pouring out the top, and I'll feel all the burbling and vibrating here. And I'll just boil it using this torch. You're gonna have to be a little patient. This takes a moment. I'm not gonna cut anything out, so let's just fire this thing up here. Boil some water. Okay. And now what I'm going to do once it's really boiling and there's steam coming out is invert it and turn it upside down into that dish of water. And if this works, you're going to have to watch closely because it's not going to take long. And then I'll explain what happened. So once I invert it into the dish of water, you want to pay close attention. Let's see here. I feel some boiling, but I don't see steam coming out yet. Yeah, what do they say about a washed pot? Okay, now we got some steam coming out. You guys see that, right? A lot of steam coming out. Okay, wish me luck. Yes. All right. Got no towels to clean up this puddle. Doesn't matter. Okay, you can replay that as many times as you want. I don't have to do it again. This can was crushed in a split second. So what did that have to do with phase transitions, and what did it have to do with atmospheric pressure? Well, our class, we're not really studying atmospheric pressure, but we are studying phase transitions. And what we had was steam. We had steam in the can. I turned the can upside down and put it in the water. That formed a seal. And because the water is much cooler than the steam condensed. It condensed very rapidly. Once the steam condensed, it left behind a vacuum. And with a vacuum there, the atmospheric pressure just crushed the can. Okay. This demo, by the way, you can see it done online. People have done this with oil cans, with barrels, with seriously large objects. But this one you can do at home. So you just need the tongs. You saw what I did. You got the tongs. You gotta wait, you gotta be patient till the steam is really coming out the top. and you invert it, and you don't even have to rush that much. You invert it, dunk it, and then you get that collapse. So there's the phase transition. What was that? It was a phase transition from steam back to liquid, okay, from a vapor, from a gas to a liquid. Okay, well, that worked. We're 2 for 2. 2 for 2. Okay, let me get rid of this. There's the proof. Oh, and one more thing. Probably a lot of water got sucked up into the can. Indeed. So water runs out because water got sucked up in. Okay. That's enough of that. Tongs we don't need. Torch we'll need later. And let's see, always come prepared. Yes, indeed. Always come prepared. Okay, we can mop that up. Okay, let's see what's next on our agenda. I'm going to get to the heat engines, these interesting little devices, but this, after all, was a bit of review, so we've done both of these. And like I said, go ahead and try these, whether you put them in your notes or not, that's fine, but try them out and see what happens. You can try either one of these and get good results. If you can document them, all the better. Definitely you have a good note about them so you can show them to your future students. Okay, now this topic here is a very interesting one. It's out of the flow of things, so to speak, but it's a bit of a review because it covers so many things that we've talked about so far. So we're going to talk about the Arizona Meteor Crater and energy in the Arizona Meteor Crater. And I'll just block out this much board here and we'll fit all the notes right in here. So first of all, with the Arizona Meteor Crater, what is it? Look it up. Look it up and get some images. So look it up. Online, of course, you get some images. And maybe you get some more information from a wiki article about the Arizona Meteor Crater. Yeah, so what it is a crater that was excavated by a falling star, as it were, a meteor. Meteor comes down, hits the ground in Arizona, right here, produces a tremendous explosion, and lifts out, I'll draw the whole thing here, lifts out so much earth that there's a crater left after the explosion. And it turns out we know enough about the physics here, we could actually estimate the size of the meteor if we knew what the size of the crater is, which is known. Okay. So I just want to run through what the physics is here. We've got an incoming meteor. Make a better picture, but I'm just going to use this board right here now. Well, actually I've got a little more board than that. Yeah. In fact, I'm going to use all of this now. We've done our demos. Let's get a little better start. Bigger piece of board here. Okay, meteor comes in, blasts a hole in the ground. So there's the incoming meteor. Comes in here, it's tearing along. Hits the ground right here. Big explosion, throws up, excavates a crater. So let's write this down. incoming meteor collides with the Earth. And excavates a crater. And there are some data on the wiki page you can look up as to this crater here. The diameter, I'll go with the radius. The radius is approximately 600 meters. The depth, we always use the letter H, don't we? For the depth is approximately approximately 170 meters plus, and I'll put this in parentheses, plus 240 meters of rubble. So the base is here, but it's known that the base is a bunch of rubble, and this actually extends deeper. So one could even model this thing as a hemisphere, hemispherical shape, because even though it's wider than it is deep, the depth of the original thing actually goes quite a bit deeper. So the meteor came in, boom, blasted all the rock out, it went every which way, and some of it fell back in. That's the way to look at it. Okay, so what does this have to do with energy? Well, what we have here for the meteor is kinetic energy. Kinetic energy, it collides here, it's immediately transformed into what? Heat, because this gives a gargantuan explosion. Heat plus work, namely the work of excavating that crater. All that earth, all that rock had to be lifted out because it left an empty crater. Okay. So what we have is kinetic energy. So let's put this first of all in words. Kinetic energy of the meteor equals heat plus work of excavation. Okay. Put a blue box around that. There we go. So now what we want to do is convert that into symbols that we've learned. So I will say I have 1/2 mass v squared. That's the kinetic energy of the meteor. It's equal to some Q here, heat. Truth be told, I don't know how much that is, but the work of excavation, I'll use a different MGH, right? That's the work of lifting something and lifting all the rock out of this hole. Okay. So I want to look at this a little more, because although the heat is just some multiple of the whole thing we don't know, we definitely understand kinetic energy and we understand work. Okay, let's see. Do I have room here? Yes. So I'm going to write 1/2. MV squared. And I'm just going to put a twiddle here. We're going to ignore the Q. There is some multiple. So that we could say the Q is some multiple of this work here, equal 1, 2, 3 times as much. So we'll focus on this here. This mass is the density of the rock times the volume of the rock times G times H. So we've been using a formula density of water when we were talking about hydropower. And what I want to point out is these things are not necessarily unknown to us. This would come from the mass of the meteorite, which is made of iron. Okay? So we'd have a density of iron, a volume of the meteorite. I want to draw attention to this speed. What is this speed here? Is this just a complete mystery, or do we have any idea how fast that meteorite is going when it comes tearing in? And we do have an idea, because we know about the orbital speed, the near-Earth orbital speed. So we know it's going to be greater than the near-Earth orbital speed because an orbiting satellite is bound, whereas this thing came from way away, so it's going to have a greater speed, greater than the orbital speed, so it has to be greater than 8,000 meters per second. And the current estimate for this that the researchers have come up with is about 12,000 meters per second, which is fine. Makes sense on a lot of bases, okay? So, but, you know, if we were just doing our estimate, we'd say, good, 10,000 meters per second. And then on this side, we could measure the meteor crater and figure out this side completely. And the V squared, we would just estimate, and so the only unknown would be the mass of the meteor, and we could actually estimate the mass of the meteor that way. I've done that before with a class, but this time I'll leave it at that. I just wanted you guys to see a good example of, you know, energy being converted to heat, being converted to work. So kinetic energy, work. Okay, so you've got that there, and definitely I would like for you guys to have meteor crater in your notes. Images, etc. in your notes and in your book. Okay. This is a very interesting topic. If you haven't seen it before, you look at that thing, you'll be amazed. You'll be glad you weren't there. Okay, good. So we've got that on our list, and now I'm moving on to the actual new topic. This was all demonstration and review in a sense. And that is going to be heat engines. I'm going to start with some demonstrations. I'll go ahead and erase all of this here. Very interesting topic. Yeah, once again, can't stress enough. This Q, we'll just say it's a factor of this here, so it could be the same amount times 2 or 3. It doesn't make that much of a difference when it finally comes down to getting the radius of that incoming meteor. Good. Okay. This will be erased now. Okay, now we have this next demonstration. You gotta wish me luck on this one, because this lecture hall has a lot of air currents at any time. And this thing is very sensitive to air currents. It's a family heirloom. It's called a Christmas pyramid. And I'm using it as a demonstration of a heat engine. Okay. And the air currents in the room can definitely mess us up, but I think I'll be able to pull victory out of this thing if you see the air currents in the room are insane. All right, let's get these things going, and we'll talk about how this thing is supposed to work. Oh, it's working pretty nicely. So this is a heat engine. It's taken the energy in the candles. They're not butter candles, but they're candles. It's creating an air current, a rising air current. That's heat transfer by convection. And it was carrying the wise men on their way. So far, so good. Now here's where I usually need someone to help me. I'm going to fashion a chimney. They're about to go backwards, but that's because of the air currents in the room, right? The proper direction when it's functioning is forwards. You can see that. I'm going to fashion a chimney. Wish me luck on this. Okay. Anything that can go wrong will, but watch this. So there's a chimney, and yes, come on. Here we go. Okay. Getting too much time. See, now the air currents in the room are sending them backwards. This chimney will right all wrongs with any luck. That's the problem. Here we go. I don't care. One take. Let's see. We got it. We get it to work now. So see the turbine is touching the chimney. As soon as I get it to not, there we go. Okay, what you'll see now is that chimney made them really zip along. Keep touching it here. Okay, okay, I'm stubborn on this because the effect is real and substantial. This, of course, is a mediocre chimney. Once more with feeling. Here we go. Okay, yeah, see if I get, the paddles aren't, okay, there we go. It was all worth it. Proof of concept. The chimney massively increases the efficiency of this thing. Okay, those guys don't know what hit them. All right, I'm gonna savor this moment. Hope I don't start a fire. Okay, that's what I was after. The chimney substantially improving the efficiency of this machine. Okay. That's a partial success. All right, left the mess on the table. We can get that later. Okay, good. So let me tell you what we have here. So the first demonstration is you know what? This thing has done its service. It's out of here. Okay. Fantastic. Good. Okay. So yeah, we're looking at what is referred to as the Christmas pyramid. Hand drawing isn't good enough for this, so also get some images of these. They come in, this is a very small, humble one. They come in large double-deckers, triple-deckers with a lot of candles, okay? A fun European thing. So you got the Christmas pyramid, and that is a heat engine. So what is a heat engine? A heat engine is a device that takes thermal energy and converts it into useful work. Okay. So a heat engine, you take thermal energy and convert it into work. You know, when we're drawing our little cartoons and stuff, we could say, this is what we want. From thermal energy, we want to get work, useful work. And so this Christmas pyramid, if I draw it, I'm not so good at drawing it, but there's a turbine, and then down here we have the wise men being carried on their way, and we have the candles here. Okay, so there's our Christmas pyramid. And we had the fuel. Then we have combustion, heat of combustion. We have the convection currents. They're going through the turbine here and spinning it around. And that's how we get the rotation here, circular motion, okay? Okay, so that's a great example. And the chimney trick was so important because the heat engine, you know, it works from, well, okay, first of all, here we just have energy being turned into another form of energy. The process, though, the convection process, the heat transfer process in general, requires that we have heat flowing, once again, in this direction. Hotter to colder. And it turns out that that chimney really makes it more efficient, because what you're doing is you're isolating your hot air section down here, your colder air at the top of the chimney, and you're getting a tremendous fluid flow, convection current, and that increases the efficiency substantially. Okay, so that was that demonstration. I think I'll finish off with the steam engine here as well while we have them all out, and then we'll analyze the thing more thoroughly. So this demonstration we saw the principles of it, fuel, convection current. We'll fill that in later some more. Yeah, so this is what, it's like an early heat engine, okay? Steam engine, it's a functioning toy. Toy? So there is fuel. There's a boiler here with water in it, and there is a little cylinder. It's got a piston inside, and we can actually spin this up. So this one's going to require also a little bit of patience, but not so much patience that I won't use the blowtorch here. So I can fire up this fuel. Why use matches, right? Fire up this fuel here. So I've got this burning fuel, and we're going to heat up the water in the boiler there, and this is going to take a couple seconds as well, during which time I can work on my drawing here. Okay, so we've got the Christmas pyramid, turbine, and now we're doing the steam engine. Different principle entirely. So the next demonstration is the steam engine. And what do we have here? We have a boiler. It's got a window in one end. There's a little water inside. I've got blue. How about blue for the water? There's water inside there. Right there. And we have fuel and a fire. So I'll just write fuel. If I have some red, and I don't have some red, but yeah. So we've got a fire burning here, and that's going to heat the water in the boiler. Then there's going to be some connection to a cylinder. The cylinder has a piston inside. The piston's connected to a flywheel, and there will be gas in here that is actually pushing on this piston, and it's going to push it forward. Now the question is, how does the piston come back again? I'll answer that in a second. This thing's ready to roll. There you go. It even can light this light on. If I disconnect this, it goes even faster. So yeah, the rest of the semester, we've got heat engine, flywheel, generator, little lamp. Everybody knows what they want for Christmas. How do we turn this thing off? Doesn't have an off switch. Fire. Put this here. Oh, the fire alarm isn't set off. Yeah, so that is a functioning steam engine. Not bad at all. Good. Functioning steam engine. So that was the last of my demonstrations for today. And from here on out for a bit, it'll get pretty theoretical. That's all right. Okay. Good. So steam engine successfully demonstrated. Here's the interesting thing. You can see the process. Got steam. It's going to push this piston turn this wheel. And the question is, how does the wheel get back? Because that's only 1/2 of a turn. Okay. And if there's so much pressure, you would have to do work against it. You'd have to do as much work as you gained by having the thing, we're going clockwise, having the thing push it forward. So I'll answer that. First of all, though, we'll have work equals force times displacement. Very good. So it's just F times, we'll use the letter D. And the force comes from the pressure here times the area, and the D is, some little length right there. So every time you get a little increment of force. Okay, so the answer to how this thing cycles is that there has to be a valve. There has to be a valve that opens and closes. So it has to open up when the piston's going to come back on the return stroke, and then it'll push that steam out. Okay, and then the valve will close, and then the piston will move forward again. So valve has to open, close once for every revolution here. So you're getting power on this time, and then spinning around again, power, spinning around. Or work more like, okay. So there's your schematic diagram for the steam engine, and the question is, where was the valve here? That's kind of tricky. So I'm just gonna hold this thing up, and if I turn this wheel, you'll see that the cylinder's rocking up and down, okay? And what's happening is the valve is shut for this half turn, and then it's open for this half turn, and it's shut and open. Now, the way it opens and shuts is when the cylinder rocks up and down, a tiny little hole is uncovered and covered, uncovered and covered, and when it's uncovered, the steam can be forced out. If you were in the class with me, I would have held this thing up, and you would have felt little puffs of steam, hot steam coming out as the thing turns. Okay, so yeah. Now you know what you want for Christmas, functioning little steam engine. And when this thing came online, as we would say nowadays, it changed civilization altogether, okay? And it was fuel to work, okay? Burning fuel, we're obtaining work. Okay. So we have these two diagrams for the heat engine. We have the Christmas pyramid, and we have the steam engine. This one is pretty good. You've got the valve. You can look online and maybe find some more clear depictions of this, but this is pretty good. For example, this I'd like you to be able to reproduce on that upcoming exam next week, which we'll talk about more. I'm not going to talk about the exam right now, but this is an example of something you want to be able to reproduce and explain, and also the purpose of the valve there. Good, I'm going to come back to that Christmas pyramid. And then I'll come back to this thing. So once again, the Christmas pyramid. So yeah, we have the turbine. In fact, I'm going to leave a little space up higher this time. So we've got the turbine, the propeller, so to speak, and then there's the whatever you want this thing to do. All it's going to do is spin for you. But we have these are the figurines, okay? So I'm going to put the candles out here with their flame. These are our candles. And we're getting that convection current. And so this time I want to draw the chimney in. chimney here, the chimney separates the hot and the cold air and brings forth that greater draft. But it's an essential feature of the, I'm gonna erase this. It's the essential feature of the heat engine that there be a higher temperature and a lower temperature. I should have noted this on our steam engine while I had it up there. The higher temperature was inside the boiler and the lower temperature was the air outside. So clearly there was a higher and a lower temperature. The chimney effect really drives the point home. If you didn't have enough separation between hot and cold, the thing would just burn up and it wouldn't really turn. It would be hot air everywhere. You wouldn't have that draft. Okay, so you've got TH, you've got TC, high and low temperature. You've got the fuel, which is then burning, so you've got combustion, and then you've got thermal energy. So you've got that thermal energy down here at a certain high temperature. It has to channel, it has to flow to a lower temperature area in order for there to be work, in order for the work to actually progress. THTC chimney, I'll just put here the chimney effect. I went to great lengths to make sure you would see it, and I'm sure you did see it. Okay, we did get that chimney effect. Okay, I think that's where we're going to leave it for today. So I'm just going to write next time, more of the theory of the heat engine. So I'll write heat engine and efficiency. This is where our discussion of entropy is going to come into play. I brought up the entropy that, it seemed kind of abstract. I brought it up because we're going to get the heat engine and its efficiency very nicely. What else do we have here for next time? That's the main thing. Heat engine and its efficiency. We'll review this stuff. As far as the homework goes, I gave you a lot of things to try and a lot of things to print out, so maybe that's not bad. Okay, you can try, here, I'll bring these back into view. Okay, you can try this demonstration. You don't have to have these blocks. You've got wood, you've got cast iron skillet, you've got all that stuff. So there you have that. This one is interesting if you've got a gas burner on your stove. You should be able to pull it off. You need those those tongs, and you can try this demonstration as well. And then you have the Arizona Meteor crater. You want to do some printouts, and possibly some printouts for this material. Okay, good. That's all for today. Take good notes and see you next time.